So let's go into a little more detail about projectile motion. So projectile motion is an extension to 2 dimensions of free fall motion. So you're going to have now a y and an x position, right? So you're going to have an x-axis and a y-axis, and then your projectile motion is going to be something like that, where you're going to have at each time, at different times, you're going to have an x and a y position. So you have two motions. You have a motion in the y-axis in the vertical direction, and you have a motion in the x-axis in the horizontal direction. So the only factor here that is causing the velocity to change is gravity. So gravity always points down. So gravity, g, right, minus g, that's the acceleration of your motion. So that's the only factor that is changing the velocity. In all of our examples in this class, for now, we're going to ignore air resistance. So the trajectories that this projectile motion are going to follow are perfect parabolic trajectories. Here we have some pictures, some frames of real balls that are dropped. The red one is just drop, and the yellow one is launch in this with a velocity in the horizontal axis. So you can see that the motion in the vertical direction is pretty much the same, right? All these lines, they coincide, right? So the motion here in the vertical direction in the y-axis is free fall. Is free fall motion, right? So this thing is free falling in the y-axis, and it is moving with a constant speed in the horizontal axis. So that's the key to understanding projectile motion, that you have these two motions. You have a motion in the horizontal axis, in the x component, and you have a motion in the y-axis, and the motion in the y-axis has acceleration. The acceleration is minus g. The motion in the vertical axis, in the horizontal axis, is constant motion. So the motion in the two axes are independent of each other. And we'll see what we mean in terms of equations later on. So here is a motion diagram of a projectile motion. So we have these guys launch from this position here. So these green vectors, they are the velocity vectors. The velocity vectors are always tangent to the path. And you can see the acceleration vector always points down. This is the acceleration vector. It's always the same, never changes. Well, it's g, it's gravity, right? So gravity never changes. So the acceleration vector never changes. The velocity vector is tangent to the path all the time. So the velocity vector has two components. For instance, this guy here, let's just draw it here. So that vector there, it has two components. It has a vertical component and a horizontal component. So this velocity Vx is always constant. It's always the same. This velocity Vy is changing with gravity. This is the only one that changes. This one doesn't change. So to analyze projectile motion, we need to look at a few things. We need to look at the initial velocity that the projectile has when it is launched. We need to look at the angle that it has when it is launched. And then things that we would like to know is how far it lands. So you launched your projectile from here. Where does it land? This distance here, this horizontal distance, that is called the range. Also, we would like to find how high does it go, right? So this distance here. And we would like to find how long does it take to land here. What is the time of flight, right? Or how long does it take to reach this point here? Those are questions that we would like to answer. And so the variables that we can control are the initial velocity and the angle that you launch your projectile with. So here is a more detailed motion diagram, so you can see I have a motion diagram here. These are my frames. So let's look at a few points here. For instance, the velocity. This component is always the same, never changes. Always the same. So now let's look at the vertical component. You have 19.6 here, 9.8, 0 here, there's nothing there, minus 9.8, minus 19.8. So the velocity in the x direction is constant. The velocity in the y direction obeys the initial velocity minus g times t. So that is the equation that the velocity in the vertical component obeys. So you have those two independent motions, you have this acceleration, and that is actually all you need to understand projectile motion. So what are the things that we need to be aware of? So imagine that you're given a problem and you're given the initial velocity and you're given this angle here. You need to be able to find the x component of the initial velocity, which is given by vi cosine theta, and you need to be able to find the y component of the initial velocity, which is given by vi sine theta. So how do you do that? Well, remember that this is your vector, and you have to think of this triangle here, and this is your angle theta. So this is your x component, this is your y component, this is the adjacent, it goes with the cosine, this is the opposite, and it goes with the sine. So that's how you solve these problems. If you're given the initial velocity and you need to find the components, that's what you do. So after lunch, then you have two motions. You have a motion in the x-axis, in the y-axis, and that motion would be the same as free fall motion, right? As if you throw the thing up and down. So it goes up, the velocity decreases, reaches a maximum point, and it starts coming down. So that is what you need to look at. So, and then you have a horizontal motion, and the horizontal motion is just constant motion. You can see the velocity never changes here. The acceleration in the x-axis is 0. The acceleration in the y-axis is minus g. So that's all you need to understand projectile motion.